Let's first look at how Monte Carlo estimation can be used for the analysis of the type 1 error rate. Suppose we already have a hypothesis testing procedure. In other words, we have specified a test statistic, t, which is a function of our random samples, and we have already specified a corresponding rejection region, or a critical value. So in this case, if t, for example, for a two-sided test, if the absolute value of t exceeds some critical value, then we reject the null. Or if the t is in some particular region, we reject the null hypothesis. Then, by definition, the type 1 error rate of our hypothesis testing procedure is given by alpha, which is equal to the probability that t is in the rejection region, given that the null hypothesis is true. In other words, the type 1 error rate is the probability of rejecting the null given that the null hypothesis is actually true. The Monte Carlo methods for estimating a probability, for example, just like last time how we estimated confidence levels for confidence intervals, can again be useful for approximating the empirical type 1 error rate, alpha. So how are we going to do this? The overall idea is very similar to before. First, we want to generate our random samples under the null hypothesis for a large number of replications. And then we would like to compute the proportion of times that the null hypothesis is rejected, given our t and c. Specifically, for each replication, j from 1 to m is some really large number, for example, 10,000. What we can do first is to generate our random samples of size n from the null distribution. So let's denote the samples from replication j by x1 of j, x2 of j, all the way up to xn of j. These samples are drawn under the null hypothesis. In other words, when x has parameter theta that lies in this subinterval theta 0. Based on our random samples of replication j, we can compute the test statistic tj, which is given by the t function evaluated at the sample's observed values. And then we can perform the hypothesis test. For each replication, we test whether the test statistic tj is inside the rejection region. If tj is in C, the rejection region, then this indicator function will return 1, indicating that the null hypothesis is rejected. It's going to return 0 otherwise, meaning that tj in that iteration is not in the rejection region, and we retain the null hypothesis. After we compute the decision for the hypothesis test, that is the indicator function of whether we reject or retain the null for each of the m replications, we can estimate alpha by the sample mean or the sample proportion. So the empirical type 1 error rate can be estimated by p hat, which is equal to the sample mean of the indicator function, whether we reject or retain the null, over the m replications. And this gives us the proportion of times H0 is rejected when H0 is the true underlying distribution. Since our Monte Carlo estimator for the type 1 error rate, p hat, is again a sample mean, so in this case it's a sample proportion, we know that its standard error can be approximated by SE of p hat, which is equal to the square root of p hat times 1 minus p hat divided by m. And because this thing is maximized at p hat equals 0.5, We know that this is always less than or equal to 0.5 divided by the square root of m. So this gives you a method to approximate what is the amount of fluctuation you can expect in your Monte Carlo estimator for the type 1 error rate, given a particular number of replications m. So now let's see an example of estimating the empirical type 1 error rate alpha. The R code for this week are given in examples week 6. .rmd. So for this week, the R Markdown file contains the incomplete R code. For some of the code chunks, you will need to fill in the code yourself. However, you can find all of the code inside our slides. Okay, so let's look at the example. Our example concerns the one sample t-test. Let's let theta denote the expectation of x, where x is a random variable. We know that this is essentially the same as mu of x, which is the theoretical mean of x. Under the one sample t-test, we would like to test the following null and alternative hypotheses. The null hypothesis h0 is given by theta is equal to mu0, where mu0 is some pre-specified value that we want to test. For example, we might want to test, is the mean of this distribution equal to 0, or is it equal to something else? Then the alternative hypothesis is just the complement of this, which is theta is not equal to mu0. Given a random sample x1 all the way up to xn, the t-test test statistic is given by t that is equal to the sample mean minus mu0, divided by the estimated standard deviation divided by the square root of n, our sample size. Here, s is equal to the square root of the sum of the squared deviation between each individual value with the sample mean divided by n minus 1. And s is an unbiased sample estimate of the population standard deviation. So you can see that here our t is a function of our data, our random sample x1 up to xn. And we're going to use the t to test whether we should retain or reject the null hypothesis. I believe you guys have learned about the t-test in an intro statistics course. So we know that on the t, that is t statistic that is defined this way, in theory, should follow the t distribution with n minus 1 degrees of freedom when some regularity conditions are satisfied. So when does our test statistic t follow the t distribution with n minus 1 degrees of freedom? Well, I'm not sure whether you guys have learned about this, but there are two assumptions that need to be satisfied. The first is when x bar follows the normal distribution with mu0 and standard deviation given by variance given by sigma squared divided by n. So the x bar needs to be normally distributed. In addition, n minus 1 times the sample variance estimate divided by the sigma square, which is the true population variance, should in theory follow the chi-square distribution with n minus 1 degrees of freedom. So you might ask, when are these two assumptions satisfied? Well, both of these can be satisfied when our samples, x1 all the way up to xn, are IID random samples from the normal distribution with mean mu and variance sigma square. In other words, under this normality assumption of our data x, the null distribution of t is the t distribution with n minus 1 degrees of freedom. And then we can apply the t-test and find what is the corresponding critical value we should use under the t distribution with n minus 1 degrees of freedom. So in this case, we can reject the null if our test statistic evaluated on our data, its absolute value is greater than t star 1 minus alpha divided by 2, comma, and minus 1. So this t star here denotes the critical value that we're going to use to decide whether we should reject or retain the null hypothesis. If the absolute value is greater than this t star, we reject the null. Otherwise, we accept the null. So this t star is the 1 minus alpha divided by 2 quantile of the t distribution with n minus 1 degrees of freedom. You can get this in R by doing Qt. The probability is 1 minus alpha divided by 2, and the df is n minus 1. However, what if our data is not normally distributed? So if we implement this t-test method and the corresponding critical value, when our x's do not come from a normal distribution, then what is going to happen to our observed or empirical type 1 error rate? Is it still going to be equal to alpha? Let's conduct a simulation study and try to examine the robustness of the t-test against non-normality. So here's how we're going to do it. We're going to consider 3 different kinds of distributions that are not normal for our xi's. We'll consider when our xi's follow the exponential distribution with rate 1, the uniform distribution between 0 and 2, and the chi-square distribution with 1 degrees of freedom. You can see that although none of these are the normal distribution, in all 3 cases, the expectation of x, which is the theoretical mean of these distributions, is equal to 1. So let's perform the t-test, where the null hypothesis is that the mean is equal to 1, and the alternative hypothesis is theta, our mean, is not equal to 1. We'll do this with different sample sizes. Sample sizes denoted by n. And we'll use a significant level alpha of 0.05. So based on this alpha value, we will find the corresponding t-distribution's critical value and decide whether we want to reject or retain the null. Let's see how the empirical type 1 error rate compares with the preset theoretical value of 0.05. So let's see how we can implement this inside R. Under each of the following conditions, so there are 4 possible sample size conditions, n equals 5, which is extremely small, n equals 25, 100, or 500, and also the 3 possible distributions of our x's. So x follows exponential 1, uniform 0, 2, or chi-square with 1 degrees of freedom. We will replicate the t-test at significance level alpha of 0.05 for a total of 10,000 times. So m is equal to 10,000. So before we do this, let's first create a matrix for storing the results. That is, we want to have a matrix where we store the empirical type 1 error rate, that is the alpha estimates, across all of these possible conditions of n and the distribution of x. Let's call this matrix type 1. It's going to be a matrix of 4 rows and 3 columns. And for each of the rows, we store the results corresponding to one of the 4 sample sizes. So our n's are given by 5, 25, 100, and 500. And let's give the rows labels by doing row names of type 1. And the row names will be given by n equals 5, n equals 25, n equals 100, and n equals 500. The columns will correspond to different kinds of distributions of x. So let's give them column names as well. So the first column will be exponential 1, the second will be uniform 0, 2, and the third will be chi-square 1. So now we have a matrix of all NAs that we can use to store the results. So let's first create a function that implements the t-test. So here's a function for performing the one sample t-test on a random sample X for a given mu0 and alpha level. Essentially, what this does is it compares the sample-based test statistic t with the critical value given by the 1 minus alpha divided by 2 quantile of the t distribution with n-1 degrees of freedom. I have created a function called t-decision. So it's going to take x, mu0, and alpha as its arguments and return the decision of whether we reject or not. What we'll first do is to find out, based on our x, which is the vector of our samples, find out what is the sample size n and what is the sample mean, x bar. And then we can compute the test statistic for the t-test. We'll call this t-stat. As we know, this test statistic is given by the sample mean minus mu0 divided by the s. So that's given by SD of x, the sample standard deviation of our x's, divided by square root of n. So that gives us the value of the test statistic. Subsequently, we'll want to see whether t-stat is greater than, or is its absolute value greater than the critical value. So we know the critical value for the t-test with the significance level alpha is given by qt of 1 minus alpha divided by 2 and degrees of freedom of n-1. So if the absolute value of t-stat is greater than this t star, then we reject the null. So 1 times this true-false test is going to be implementing the indicator function. Otherwise, so if this is less than or equal to t star, we do not reject the null, and it's going to return 0. Now we can perform the simulations under each condition. Let's first do it for the case where x follows the exponential distribution with rate 1. As we said before, we will replicate this for a total of 10,000 times. So under this distribution of x follows exponential 1, we need to consider several possible sample sizes. So n equals 5, 25, 100, and 500. And that is stored in the ns vector we created earlier. For each of these possible sample sizes, we will first create a decision vector that is a vector of all zeros with length equals to m. And then we're going to replicate the hypothesis test for m times. For the j replication, we first simulate our samples under the exponential distribution with sample size n and rate 1. Then we use the t-decision function we just created to test the hypothesis and see whether we reject the null or we retain the null. And we'll store this in the decision vector we have created. After iterating this for a total of m replications, we end up with a decision vector where each entry is 1 or 0, indicating for that replication was the null hypothesis rejected or retained. By calculating the mean of this decision vector, we get an estimate of the empirical type 1 error rate for that particular sample size condition. So we store that in the type 1 matrix we created earlier. So the ith entry, which corresponds to the sample size condition, and the first column is going to be equal to mean of decision. So after looping this, we can take a look at the values of the empirical type 1 error rate under each sample size. So here is just printing the first column of the type 1 matrix. So the idea is that we can do the same for the other two possible distributions of x. So that is the case where x follows u02 or x follows chi-square with 1 degrees of freedom. In our markdown file for this week, the code for these two cases are left blank for you to complete. I am going to present the code for these on the next slide. However, I believe you may try to implement these on your own using the code for the exponential 1 case as a reference. You can store the results in the second and the third column of the type 1 matrix, respectively. Okay, so let's look at the code together. Here's the code when x follows the uniform distribution between 0 and 2. Everything else is the same, except that our x's, which is our samples, are simulated or randomly drawn from the uniform distribution with a equals 0 and b equals 2. And we will store the results in the second column of the type 1 matrix for different sample sizes. And here's the results printed for the uniform 0,2 case. And lastly, here is the code for doing this for the chi-square distribution. Again, everything else is the same, except that we sample our x's from the chi-square distribution with 1 degree of freedom. And we store the results in the third column. So rather than looking at the results separately, let's look at the overall results across all three possible distributions of x and all possible sample sizes. And let's see how close the empirical alphas compare to the theoretical value of 0.05. Everything is stored inside the type 1 matrix, so we can just print the type 1 matrix rounded to 3 digits. Each of this gives us the empirical type 1 error rate. That is the proportion of times the null hypothesis was rejected when the data actually comes from the null hypothesis. What you can see is that although for larger sample sizes, the empirical alpha is close to 0.05, especially for really small sample sizes, the empirical type 1 error rate is quite far and a lot larger compared to 0.05. And this is known as a type 1 error inflation. As our sample size increases, the empirical alpha approaches the significance level of 0.05. One thing you should note is that as the sample size goes to infinity, we have the central limit theorem and the Slutsky theorem, which tells us that both the t statistic and the t distribution with n-1 degrees of freedom should converge in distribution to normal 0, 1. Another thing to note is that you might have heard the notion when you first learn about the t-test that the t-test is relatively robust to moderate violation of the normality assumption. However, as you can see from the simulation results here, for highly skewed distributions, so especially for exponential 1 and chi-square 1 over here, which are both very skewed distributions, and very small sample sizes, so for example, n equals 5, you can see that assuming the test statistic follows the t distribution with n-1 degrees of freedom might not be very appropriate. For the symmetric uniform distribution, we can see that it's a little bit better. So we have demonstrated using the Monte Carlo methods how we can evaluate the empirical type 1 error rate of a hypothesis testing procedure. That was the case where we were given, so we already have a test statistic and a rejection region, which we believe theoretically should achieve a type 1 error rate of alpha. And We simulate random samples from the null distribution, and we compute the test statistic that is given and compare it to the rejection region and see whether each time we should reject or retain the null. And then we can calculate the average, so the proportion of times that the null is rejected, and that will be our empirical type 1 error rate. So this is one way that the Monte Carlo methods can be used for type 1 error analysis. So when you already have a procedure you developed, you want to see how it performs under various conditions, then you can try to evaluate the empirical alpha and compare it to the theoretical value you think it has. In practice, Monte Carlo simulations can also be used to numerically approximate the critical value or the rejection region that achieves a type 1 error rate alpha. I will not give an example of this, but I can give you an idea of how this works. So, as I talked about earlier, a lot of the times the exact null distribution of our test statistic, especially when it looks unconventional or when the sample size is small and we shouldn't apply the asymptotic results, is hard to derive. In these cases, we might not know what is a theoretical critical value or rejection region we should use to achieve a type 1 error rate alpha. In these cases, you might try to use Monte Carlo simulations to determine, given a particular test statistic that you have constructed, under the null hypothesis, what value should you use as the cutoff to determine whether you will reject or retain the null hypothesis if you want to control your type 1 error to be approximately alpha. In other words, we would like to find, given a test statistic t, which critical value c will achieve the type 1 error. So p, for example, the absolute value of t is greater than c given h0, closest to alpha, say, equals 0.05. And you can do this using a method we will talk about later in this class. So when we talked about optimization, and that's known as grid search. The idea is actually quite simple, which is I am going to assume that there is a wide range of possible C values I can use. So for example, C equals 1, 1.01, 1.02, etc., all the way up to 2. And then you're going to try with a wide range of C values. For each of the possible C values, you evaluate the empirical type 1 error rate of your test statistic and the hypothesis testing of whether your test statistic is greater than C, etc., using Monte Carlo simulations. So for each C, you will be able to get an empirical type 1 error estimate. You can then see what is the best C value for you to achieve a type 1 error rate that is closest to the alpha you want.